Yeah, I'm going to talk about machine learning, just introduction to it, and yeah, kind of bring us closer to more of the deep learning things we want to get into. So this is kind of things I want to go over, training testing data, what cross-validation is, some models, as well as regression and classification metrics, principal component analysis, gradient descent, and gradient boosting, and XGBoost. If you want to learn how to use a lot of this stuff, it can be used in Scikit-Learn. So that's like typically what you want to do if you want to learn English. Look up Scikit-Learn tutorials for any of these, or look up the documentation for Scikit-Learn as well. So so you, Sophic, last time introduced like what machine learning is. So I'm sure you all know it's supervised versus unsupervised versus reinforcement learning, all those types. So now I'm going to kind of get into the data part, like how do we actually use data? So data generally comes in two forms, where it's unstructured and unstructured. Unstructured, the structured is like basically your Excel spreadsheet. You have columns and rows. Unstructured would be something like a video MP4 file or an audio waveform, an EEG signal, things like that, which you then want to clean and then turn into pre-processed data. And so we need to pre-process our data because models can only deal with numbers themselves. They can't, if we give it like a string, it doesn't really know what to do with it. So then we have different operations for different things. For numerical values, we can normalize or standardize them. And ordinal, and for categories such as like gender, race, and like maybe country, we can do ordinal or one-hot coding. And if you're doing dates, you can also bin them as well. And so once you have the pre-processed data, you then want to split it into really two main types of data, but the third one as well. This is where the Scikit-Learn train test split comes in. So you have training data, which is what we use to train the model, but then you have testing and validation data, which are used separately to evaluate the model as well. So as you give the model training data, what it's going to do is then going to tweak its settings and parameters. So each model has its own set of parameters. And then as it learns from the training data, it's going to have some kind of error, which is essentially how many mistakes it makes. And we want to quantify that somehow. And it's going to use that error to then tweak its settings a certain amount. And we'll get to gradient descent and how that actually works a little bit. But this is kind of the workflow for how training and testing goes. So cross-validation, it's a way to kind of measure how well our models perform. And so there's a specific problem when you deal with these that first comes up, is called overfitting, where the model itself it learns from the data, but it learns too specifically. It's like kind of constraining itself to the data. It doesn't generalize well. That's overfitting. And so one way we can minimize that is to split the data into K smaller sets. And it's also called K cross-fold validation as well. So the model's trained, as it's on the figure, it's trained on K minus one of the sets. So the first folds 2 through 5, and then the model is tested on fold 1. And then you're going to keep doing that, but it's going to keep looping through each of those folds, and then it's tested and trained on essentially new pieces of data. So it's trained on new pieces of data, and then a final performance is averaged of the K set. So that's how that kind of works, and that's how you do it in Scikit-Learn. For linear regression, this is just the classic example of regression. So you have some inputs, and you want it to output a continuous value. That's the regression part. So for one variable linear regression, you would have y equals mx plus b. That's the basic version. And what it's doing, as you can see here, the red lines is going to represent the error between what the line predicts and what we want it to predict. So it's the errors. And it's going to tweak the m in order to minimize that. So m is going to be its parameter that is training. The error is going to be the distance between the output values and the line predicts. And it's going to want to do to minimize the overall error somehow. And typically, we're not dealing with only one input variable, we're dealing with multiple variables. So this is where multiple linear regression comes in, which you can have different amounts of m's and y's and z's. So for higher dimensional kind of learning, and you kind of generalize it with like a vector. So you could do the dot product of the weights. By weight, I mean the parameters, so the m and the inputs, and that would give you a value. You wouldn't actually add a vector then. In that case, b would just be one value. But it's just mainly trying to generalize the top value y. And also, if you have any questions, just feel free to ask them in chat or in person. So K-means clustering. This is an example of unsupervised learning. So What you want to do is you want to get your data, but we're not going to tell you what classes it is. So it's going to try to form K-clusters around the nearest means of the data. So what I mean by a mean of the data, it's like where the data is most concentrated. It's then going to try to split it up into the different classes like that. And once it's trained, so once the K-means cluster is trained, you can then use it for classification as decision boundaries there. Support vector machines. So this is an example of an unsupervised learning model, a supervised learning model, sorry. And kind of how I would describe it is you're kind of fitting the widest possible street. So the support vectors themselves are kind of two lines that try to split the data. So normally, instead of having just one line, we would have two lines. It's kind of trying to split it farther. So it's supposed to try to be more precise than our regular decision lines. And in two variables, it would just be a line, but in three variables, it would be a plane. So it would be two lines or a hyperplane. And it's just trying to maximize the distance between lines. That's kind of the overall optimization goal. And it's typically not used in very big data sets. It's mostly small, complex, medium-sized data sets. So random forest itself is an algorithm that uses a bunch of decision trees. So a decision tree, it's just basically kind of how it's like kind of goes down different. It's like a tree starts with a root and then it goes down different nodes. That's going to tell you how to make decisions on the leaf, so at the bottom of the tree. And for example, it says outlook. You could have, if you want to play tennis, you could have it if it's depending on the weather, depending on the humidity and the wind, you would have different values. So what it's going to do is going to create different nodes and leaves depending on the task we want to train it for based on the data. It's going to keep doing that. So that's one decision tree. And so the way you ensemble them together is you basically take a bunch of the decision trees and combine them into then the random forest. And then it does so then it does majority voting, and it kind of wants to combine the predictions of each of the smaller trees to one big prediction. So it's the final prediction. And typically it's going to be much better. So if you have one single decision tree that doesn't do super well, if you combine it with like hundreds of other decision trees that also don't do super well, it'll increase your performance by at least a few %, because you're kind of looking at the model. You're kind of like training models from different perspectives in a way that increases your overall performance. And one cool thing about random forest is that there's a relative feature of importance you can get that's unique to this model. All right, regression metrics. So there's three main metrics and how we evaluate regression models. So as I mentioned earlier, we take the distance between the output values and the line we made. So that's just the mean error. And so we would average them all out, but absolute error just kind of take in case if it's negative or positive, we want it to be a positive value. So it's just normal units and it rises linearly. However, if we want to punish the model for performing bad, especially on the large errors it has, then we would use mean squared error. The issue with mean squared error is it's less interpretable because it's using squared units. So there's the 1 over n is the squared. So then to fix that problem, we can also use root mean squared, which is the same thing as mean squared error, but it outputs normal units because you're taking the square root of a square. So then it gets back our normal units, which is more kind of interpretable if you're presenting this. All these three are good. How typically mean squared error and root squared error are typically more used. Okay, classification matrix. This is the whole thing. So I'll probably ask to the room in the chat, what do you think is the difference between accuracy and precision? What's your name again?
Me?
Yeah.
Sona.
Sona, what do you think is the difference between accuracy and precision? So if I have a dartboard and I try to hit the middle of it, what's the difference between?
I guess precision is. I just say it's like a subset of being accurate. Like it's more exact.
Okay, so the exact part is right. So that would probably be accurate. So if I have an accurate throw, that means I hit the bullseye, right? And so the difference between accuracy and precision there, precision is if I were to throw it multiple times, it all those throws are closely linked together as long as I throw. So if I'm trying to hit the bullseye and they're all around the bullseye, then I have a high precision. But accuracy is how close I am to the actual, like the value you want to get. So accuracy can also be defined as the ratio of correct predictions to all predictions, and I'll show a whole table in a second. But the issue with just using accuracy for your metrics is that it can lead to a false sense of performance. So like if you have an MNIST, you have a 10% chance of, if you just have a 10% chance of randomly guessing anything, you can get it 10% right at the time. So in that case, purely using accuracy might not be the best metric. So you can also use different combinations. And precision, the way you interpret that is when your model claims as a class is classified as blank, it is only correct blank % of the time. And so this is kind of confusion matrix. This is how we kind of numerically graph it, or numerically describe it. So accuracy in this case is the true positives plus the true negatives divided by everything else. So the true positives plus the true negatives, true negatives divided by everything else. And the precision is going to be your accuracy of your positive predictions. So you are right in that the precision is subset of accuracy, but it's more how accurate the positive predictions are to each other. That's kind of the main difference. So precision, if you take the predicted class on the left side, it's going to be the top row of the confusion matrix. What I mean by that, it's the true positive divided by the true positive plus the false positive. So it's the row. Whereas with recall, that's going to be how the ratio of correctly detected positive instances. And so that's going to be the true positive divided by the true positive plus the false negative. So in the confusion matrix column, the confusion matrix is going to be the first column. If we have a predicted class, it's going to be the first column right here. So you divide true positive by the first column. That's kind of how I remember it. So precision would be true positive divided by the first row. Recall would be true positive divided by the first column. F1 score is also a really important metric. So that's just basically averaging precision and recall. It's averaging precision and recall, giving more weight to lower values. So it's basically like trying to detect anything bad that could happen with the model and getting accurate predictions. So it would definitely be higher precision and recall because the average of them. And then there is another metric called AUC, the area under the curve. So if you wanted to graph the true positives against the false positives, this would be a better way to explain it. If you graph the true positive rate plus the and the false positive rate is your X variable, a perfect classifier is just going to be like it's going to be kind of like a straight elbow, whereas in practice, classifiers are going to be kind of more curved. And this kind of tells us as the number of false positives increases, how much the true positives increases. So there's obviously a trade-off depending on which task. So if you're doing like a medical task, you'd probably care more about the true positives than false positives, right? I would imagine. So if it's like a medical classification, you'd care more about the true positive and the false positives, right?
Yeah, we care about more about like,
you want to care about detecting it.
Yeah, we care about like if we care about the false positive and false negative, so that we know if the algorithm is not like overfitting or underfitting in those conditions.
Yeah. So that's the ROC is just the receiver and operator characteristic. So there's different trade-off between these metrics. This is a very common graph you'll see in a lot of papers, a lot of things, projects, things like that. That's kind of the main ways how you evaluate classification metrics. So there's a thing called, to get into principal component analysis, there is an issue with high dimensional data. It's like if you have high dimensional data, first of all, it takes more memory to use. So if you have like gigabytes and terabytes of examples, it's not going to be efficient to store, especially given that storage costs a lot of money, especially in the cloud with servers, so it costs money. There's also risk of like, if you have high dimensional data, not all of it is necessarily in each dimension is going to be as representative or as accurate. So like, And the data in dimension 4 might not be as important as the data in dimension 3. So this is where we're going to use two techniques. One of them involves projections. So you should probably learn from like some math class or geometry, or I think Math 200 teaches this. To project a vector u onto v, it's kind of projecting like a vector with the slope onto a straight line. So it's less information stored. And so what principal component analysis does is you want to project the data into the axis that you want to project it into a lower dimension while also preserving the maximum variance, but minimizing the mean square distance between original data sets. So in practice, it's if we have something like a Swiss roll, this is a common example. It's like, give an example. So if you have like a paper like this, you have a Swiss roll that's curved. There's two ways of kind of making this lower dimensional. You can project this and kind of like flatten it. So that's what a projection does. That's kind of what the vector equation I showed you there does. Or you can do manifold learning where you can just unravel it and put it down. That's kind of the best way I can describe it. That's an example of unsupervised learning as well. And with Scikit-Learn, there's a specific method that I should put it there, but it allows you to like to get rid of like a certain percentage of the data while also keeping the variance. I think it's like if you want to keep 98% of the variance, you can remove some data. So I've seen this used in NIST before to kind of reduce the size of the digits in that data set, and performance doesn't drop by too much. So it's in practice something that could be used well. All right, so this is probably the heaviest math slide, is gradient descent. So I mentioned earlier, if we go back to the beginning, I mentioned that the model tweaks its settings with an error. So what exactly is the error? That error is found by gradient descent. So what you want to do is you want to pick some kind of error function. Like earlier, I talked about the mean squared error, the mean absolute error. You want to use that and kind of use that with the parameters themselves. So if we have some parameter theta, then the way we update it, at least with gradient descent, is we take the current parameter is going to be the previous parameter minus this whole part of the function right here, where this variable eta is going to be the learning rate minus the gradient of the mean squared error. So the mean squared error, I'll probably just write it up here. SP over n, so it's I think I used m. There, yeah, mean squared error 1 over m, and it's going to be your input values times your parameters. So the distance between what the model predicts and the actual value of y should be, let's square that. And so how do we find the triangle, the gradient? The gradient is an example of, it's a vector of derivatives, but it's really just the derivative. So if you remember from, I guess, calculus, this example using chain rules. So say I want to take the derivative of the mean squared error with respect to the parameter. This is just a basic chain rule. So this you can kind of treat, the sum doesn't, like, you don't have to worry about it. You can kind of treat it as 1 over m x squared in a way. So this part right here, this part you actually do need to take. So it's not x, it's actually, it would be, in this case, mx minus y squared. So how you take the derivative of this, the 2 comes down here, so it's 2 over m, and then 2 over m, then there would be times m as well. But because m is going to be a vector in this case, I'm not going to do the scalar comparison. So what this is going to be equal to is 2 over m. So if you're doing with theta, then the x wouldn't matter. But if you're doing the overall gradient, then that means we're not differentiating. So x stays constant in this case because it's theta, but theta is the constant part, x is the variable. So x would go here, and in this case, when we add them all up, we're just adding the parts of the vectors x. You need to transpose if you want to multiply the vectors together. You need to multiply a row and a column with matrix multiplication account. So that times theta, the inside stays the same, but the square kind of moves down. So that's what this is. And then you can kind of like combine this. So what the theta is going to be the previous theta minus learning rate times this whole thing. Yeah. This whole thing would go down here. And every step of learning rate is going to kind of adjust. This is kind of just a general model. Some of the models use slightly different values. So I think gradient boosting uses the differential one. It uses a slightly different one, but this is kind of the idea behind gradient descent. So there's two main ways of gradient descent. There's batch gradient descent and stochastic. Batch is training each parameter at once. Stochastic is kind of picking a random parameter to train. They have batch. Stochastic gradient descent slightly performs over batch. And yeah, really this theta right here it would normally keep the x constant, but because this is a vector, there's slightly different. That's kind of how gradient descent mathematically works. Every step, it's going to update its parameters. So you can kind of intuitively think of it as like the current parameters are the previous parameters minus how long those parameters were at producing the output. That's kind of what that is. But yeah, if anyone has any questions, it's kind of probably the most confusing slides. But, yeah.
Check in the chat section if somebody has.
All right. Gradient boosting. So I mentioned earlier random forest. This is going to be kind of similar, except I think it actually outperforms random forest in most cases. You take a bunch of weak decision trees. So I mentioned ensembling earlier, but what you want to do is you want to put them together, but instead of training the whole itself, you're going to individually update its parameters in each of the models. So, for example, for bagging, gradient boosting, each model would have an equal weight, and then it would be compare its outputs, and then each of the models would then tweak. So there's like kind of two different ways to look at it. There's the model level and there's the unit level. So they're kind of combined there. There's also boosting where models' outputs are fed into each other. So this is kind of classifier 1's fed outputs in classifier 2. They're kind of connected. And this boosting is kind of like together. The way we kind of use chain rule there. So that's kind of where it connects. And typically what you want to happen is as you introduce more and more trees, what's going to happen is the error is going to go down. And XGBoost is kind of the example of this. This is often, I see in a lot of machine learning competitions, it's often first place, or at least some kind of ensemble. It's always first place usually. I mean, I know we used ensembling for one of our papers earlier, but yeah.
Why is it always first?
What?
Why is it always first?
Well, it's not always first. It's just generally performs well. It's often. It's just I've seen it used. It had good accuracy just because for XGBoost, it's gradient boosting, but it uses regularization, right?
Yeah.
So that's why it kind of generalizes better.
Because it goes like step by step each gradient.
Yeah.
That's why.
Something's right. It goes step by step to create that. It's kind of like the way you think about it is you have smaller, weaker decision trees that you then combine to increase the overall performance of the smaller, weaker models. You have like an army of smaller models, less accurate models that are going to add their predictions together to get a better overall prediction. And there's those ways of aggregating it. Outputs, it has its own Python class. But yeah, I think that's all of it. If anyone has any questions now, that would be a good time to ask them. Otherwise, if you like watching this, that this was as intuitive that I could make it.
I have a question. I mean, like, I guess just for people who anyone who doesn't know machine learning, how would you know what metrics and what models to choose from? Like, how would you know to do random forest, not decision tree?
So, assuming you're using it for a classification task, then I think the best way is just to try all of them and see which one has the highest accuracy. But I think like typically random forest and XGBoost I see used pretty often as like the first main go-to Like I'd probably use that over like linear regression, maybe, or logistic regression.
Why?
And I know logistic regression has like its own separate like sub things, but
Thank you.
that is a good question, especially like if you want to like practically do this.
Also, can you explain a confusion matrix real quick?
Yeah.
Yeah.
So the confusion matrix, it tells you the predicted class and the true class. It kind of is a way to get more information on how accurate, how good your model is with classification. So true positives, false negatives, and true negatives. And so accuracy is going to be how close you are. Accuracy is the true values divided by everything else. Precision would be kind of the first row in this confusion matrix if you have a predicted class on the left. And recall would be the first column. So that's kind of how that works. And they're all really related to each other, all the little metrics. But yeah. Is there a specific part you want me to explain?
Maybe about precision, like you went, so for precision, you basically look at the first row, you said?
Yeah, you can like explain like, this part.
Yeah, I'm a little confused about how precision works.
This one.
So how precision?
Like this part. Just you can take like this part, like what is sensitivity, specificity, and like in terms of like the values. So
Sensitivity, specificity.
that's I think that's a precision, and that's a recall, and that's a specificity.
Okay, what are we looking at?
So what's the? You want me to like explain that more, like how it's used?
I just like give the formula so people could understand better.
For what?
You want this for sensitivity and specificity, right? Because the first, on the column you showed me, the first two are that's precision and recall. Right?
Yeah.
Yeah. So I said precision was the true positives divided by the true positives, false positives.
Yeah. Okay. So just do that for like all of them.
Oh, for all of them.
Just write it down here, so that's clear.
That would be cool, yeah, because the
It just becomes easier to
really
understand.
hard, yeah. So precision positives divided by
True positive is false positive.
Positives plus false positives.
I actually have a question too when you're done.
True negative over false. True negative over true negative plus false negative.
true negative. So for recall,
Just give me a second.
yeah, double time.
I also have a question for people who are new. So when you're when you're evaluating when you're evaluating these questions for classification, like which out of the three should you be more focused on?
So which out of the three? I think usually F1 scores like typically what like people what's usually what people like to do. AUC, I know we used AUC for one of our competitors. Yeah, I mean, there are cases where you would probably use, I think in most cases, F1 score and the AUC is like what I would go to.
So AUPR is very much used.
Area, what's AUPRC?
AUPRC is area of precision recall curve. So you plot precision on the end.
Oh, you're
No, it's precision and recall. So that would basically tell you, yeah, you can pop it.
Yeah, it's a good idea to put that there.
Yeah, it's a really nice way to understand. Yeah.
Okay, so precision over recall, and then that area, what does that give you then?
It basically tell you how. Okay, so it's basically so you know how precision is true positive. So your precision would be really good like you would be really good with it if you had 0 false positives and everything goes to 1, and your recall would be the same thing. So it starts there, right?
Yeah.
You can make a diagonal line. And if it goes below it, it means it's doing bad. If it is going, that means it's generalized. And if it's over it, it means doing good.
So like typically like a perfect model would be the straight diagonal
Yeah.
across here.
Yeah.
So
It kind of makes sense, right? Because
yeah, there would be something like this.
yeah, you can look up like if you see more examples on Google, like
Precision. Oh, so like that's
Yeah.
that's different.
this one on this one. Yeah, this one.
This one.
That's a good one.
Okay, so that makes sense. The perfect model is good.
It says an opposite to AUC curve. You get an elbow like this. In AUC, you get in this.
Okay.
It's a downward curve instead of an upward.
So would you then want to just use both and compare?
Yeah,
them?
you usually use both. It's a really good idea to use both instead of just using one. PRs.
PRC.
PRC.
And then there was 2 other you wanted to show me. There was 2 other you wanted me to write.
If you pull up on my paper, I did both of them. Wait. It's called wait.
Is it online?
It should be. I showed both of them, so it's so good. You can.
So it's on your
Go on to diagnostic one, the coded one.
this one?
Yeah.
Gradient.
So I use like the gradient boost too. So if you go down, see here, I have used both an AUPRC curve and ROC curve.
So your AUPRC was significantly less. So what did that does that mean like in terms of the paper?
So it basically means it basically gives you a good analysis of the model in terms of overfitting and underfitting, because it's primarily focusing on your false positives and false negatives. That is the basic. Pretty premise. Sorry, I throw it's fun.
So what are the curves in the internal model? Was it good or?
It's good. Yeah.
So does the lower one means it's less overfitting? It's what?
Yeah.
Let's say the overall like.
So you don't want it to go like downwards. The curve should be something like this. And the more you feed it with the data, more like smooth in it, like rather than break.
Yeah, that's a cool application though, just seeing it used in real paper. I think I know we use the UC, but it's good to see both of them.
Yeah. And then you can also, if you go down, you can see like how good the XGBoost does against the others. That's your AUC curve for the random shapes.
Oh, right. So this is XGBoost.
No, I guess, yeah. I guess.
So there's the other one. Okay.
No, there's just a table with all the models getting compared.
Yeah, there was a table above.
No, it's not a
That's the only table.
Really? Oh, never mind.
Whatever, but yeah, it was cool to see both graphs. But yeah, anyways.
Oh, it was, yeah, my bad. That was in the other.
Yeah, these you said you wanted to write 2
Yeah.
others here.
Yeah, that's good enough. You can write sensitivity, which is just like true positive over true positive plus false negative.
Positive plus false negative.
That's basically a recall. I'm sorry, my bad.
Oh, so sensitivity is another
You
way.
can write true negative if you clear that specificity, right? That's my bad. Specificity, which is true negative over
So what does that mean?
true negative plus false positive.
So what does that mean?
Okay, so you're swapping. Okay.
And then there's one final thing which is called negative predicted value, NPV,
Negative predicted.
which is true negative over true negative plus false negative.
Okay, so here you're kind of swapping the positives.
Yes.
So what do those mean?
What do that mean? So if you see precision and
No, specificity and MP.
yeah, so for first and fourth tell you how good are you in actually getting true positives and false and true positives, true negative. And the second and first and fourth. Wait, can I? If you say 1 and 4 here, like number it down. Just say 1, 2, 3, 4. So the one and 4 gives you how good you are in actually predicting the true values, and you want this number to be high. But in the second case, in second case, you're talking about when you're predicting the true positive value, how good are you doing in terms of the false negatives? So it's just like give you a more holistic understanding of the whole. It's just to better understand the whole situation.
So these two are more holistic then.
Yeah, like if you usually print out all of it, right? Like you say precision, recall, specificity, and then you can plot it like precision, a lot of specificity stuff.
Okay. Yeah. Yeah. Any other questions?
Actually, I do. So like the specificity and NPV, like what curves would those be for?
And NPV.
Like like the APRC for precision recall.
You can get the same thing. You can get area under NPV curve. AUNPV.
So which one out of all the curves are common? Just AUC.
I think most of them are used. AUC, I've seen AUC, AUPRC, AUNPV. Like if you look up good papers, they present you all the curves.
I've never seen NPV before.
But you can Google up AUNPV.
Not the only one that's ever heard
Or
of that.
and say ML. You said UNP. Yeah, never mind. Yeah, it's the first one.
Am I the only one that's ever heard of that? NPV.
No, that's
No.
Am I the only one that's never heard of that before?
I mean, obviously not. Here I am.
Or you can like area under. Say area. Or you can say area under. I guess predicted values. Here. And stuff like
Wait, then what's sensitivity?
values. Sensitivity of code was recall, right?
Oh, is it? Where to
Yeah, it's just words.
Oh, so it's recall and specificity. Okay.
see, like in that case, they give you like everything, like sensitivity, specificity, PPV, and NPV.
Actually, I do know NPV. Oh, I'm going to probability.
SMP and PPV.
PPV is like true positive.
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 So that basically a precision is their positive value, predicted positive. Predicted positive value.
Do I remember that?
That is a, you can say that on the first message. Yeah.
Good job.
Yep.